here with respect to modular arithmetic. So we have a natural number defined in its decimal form. The subscripted a's are decimal digits between 0 and 9, integer value 0, 1, 2, 3, all the way out to 9. So it's just, this is the expanded form representation of n. And we're supposed to show that n is congruent to this, just this piece right here, the tens position summed with the units position, mod 4. And it's based on a pretty straightforward lemma. The lemma, I just wrote it right down underneath, and you can almost just see this numerically, but it turns out 10 to the n is congruent to 0 mod 4 as long as it's a integer greater than or equal to 2. And y'all, just for what I mean by congruence, like for example, 20 minus 8 is congruent to 20 minus 8 is congruent to 4. In other words, 20 is congruent to 8 precisely because 20 minus 8 is 12, which is a multiple of 4. Okay, so you can think in terms of multiples of 4 or divisors, however you want to think about it. But right here, it's pretty easy to see why this is true just numerically in your head. But I went ahead and wrote down the lemma right here. 10 to the n, 10 factors to 2 times 5, right? And so laws of exponents indicate that 10 to the n equals to 2 to the n times 5 to the n. But you can factor a 4 out of there and use laws of exponents. And in this way, we explicitly see that 10 to the n for n greater than or equal to 2 is a multiple of 4 here. It's a multiple of 4. Now, y'all just think you see it, but 4 is just the same as 2 squared, right? Let me, marker's not working very good as usual here. So that's 2 squared right there. 2 squared. And by laws of exponents, you can see why that works out, right? So what we've demonstrated right here is 10, if 10 to the n can be represented as a multiple of 4, that means 10 to the n is congruent to 0, because that would mean 4 divides 10 to the n minus 0. Now, the notation for congruence, some people think it's too much trouble. I personally think it's worth it. It's, you can think of congruence as just like an equal sign, basically, most of the time. But this fact right here really comes in handy. 10 to the n congruent to 0. See right here, you simply, if you think of this as just an equality, that forget that it's a congruence, you literally replace 10 to these powers greater than or equal to 2 with 0, which is what happened right here, okay? But notice 10 to the first doesn't fit this lemma, because that would be for n equals 1. And also, you just can see that 4 does not divide 10. So that's how we get the result, y'all. N is congruent to the tens position plus the units position, okay? Now, we actually use that fact. I just did a concrete example right here. Again, you could do all these numerically in your head, but it's just nice to have the result written down, in my opinion. So 798 is congruent to 98 mod 4. Since 798 minus 98 is 700, but notice this is just equal to 4 times 175. Let me put a dot there, times 175. So y'all, that's it. I thought it was kind of neat. This establishing this simple lemma right here convinces you that it's true, even though arithmetically you could just do this. But now you just have a formal statement of what's going on right here. Anyway, I hope you enjoyed.